Hey guys, Mr. Rast here, and I'm here to help. I mean, that's my goal in life. You know what I mean? I'm here to help you, and I'm going to give you some help right now, some advice on an excellent pickup line to pick up the chicks or the dudes or whatever it is you want to pick up, as long as they understand English. I don't think it'll work on animals, besides humans. Here's the line. You tell that significant person, "I wish I was adenine, because then I could be paired with you." Like it, huh? Because adenine and uracil are RNA base pairs, and they pair adenine, uracil. I'm so lonely. Anyways, hey guys, topic 13, lesson 3, different types of equilibrium constants. So there's going to be a lot of pausing in this video, and I'm going to ask you to pause and work some stuff out and pause and work. It will be a little choppy if you actually do what I'm asking you to do. So let's get started here. So, like I said, I want you to write the equilibrium expression for this, and pause the video and give this a try. Remember, don't worry about the underlined thing here. I'll explain that in a moment. So pause the video and try to write the equilibrium expression for this right here. And hopefully you did, and this is what you should have got. Okay, so the KEQ for this is the products over the reactants. So it should look like this. Now, this is the standard form of Ka, the acid dissociation constant. Notice that the reaction is simply the dissociation of an acid. So in this case, the KEQ, the chemical equilibrium expression, is actually a Ka. Now, you might be wondering at this point, the simple dissociation of an acid, how do I know what an acid is? How do you know something is an acid? The most basic definition, I will get into acids and bases more in topic 14, but the most basic definition I can give you for this is that in water, aqueous, if it produces a hydrogen ion, things that produce hydrogen ions in water, aqueous solutions, those are acids. So since this produced a hydrogen ion, this is an acid. By the way, this is acetic acid. It turns into the hydrogen ion and the acetate polyatomic anion. So this is acetic acid, which is the acid found in vinegar. This is vinegar right here, and it is in equilibrium back and forth here. So that is a Ka. You have to put the acid first and then the ions. You can look up like a Ka for acetic acid, and you'll have a value. You can just look up Ka acetic acid. You'll have an actual number for this. They won't show you the equation. It's understood that the acid is dissociating into the acid here. The larger the Ka, the more of the hydrogen ions. See, if it's a large Ka, that means you have a large numerator, and that means you have a lot of hydrogen ions. So the larger the Ka, the more acidic it is, the more acid you're going to get out of it. Okay, write the chemical equilibrium expression for this one. Pause the video and do me a favor, really do this. This one might be a little tricky, so see what you do. So pause the video and give this one a try. And hopefully you did. And here we go. This is what you should have got on this one here. Notice that the water is not listed, because why? Water is a pure substance. We only list things that have concentrations. And although water does have a concentration because there's some ammonia in here, it's so concentrated, it just really throws off all the calculations to even include it. So it's not included, or it doesn't affect it, I should say, because the K will adjust for that large number. So, or you know what I mean. So it's the products over the reactants. Now this is a Kb. This is the equilibrium constant for a base, and it's a dissociation of a base. How do you know this is a base? Bases produce hydroxide in water. So like hydrogen ions are what's formed from acids. Hydroxide ions are what's formed from bases. So if you see a hydroxide ion formed, that's a Kb. Write the equilibrium expression for this one. So give this one a pause. This one's a little bit easier. I don't think there's any tricks in this one, but do that. And now we'll take a look at what you should have got. Notice in this, we have products, water and sulfur dioxide on top, and the coefficients, don't forget those coefficients go to raise those concentrations. And then you have your reactants on the bottom. There's a 2 coefficient here, a 3 coefficient here. Now, something important to remind us about, we've seen this before, these brackets are not parentheses. The brackets represent molarity. And because it's molarity, we are talking about the concentration of things. So this is a Kc. This is the concentration. And by the way, the Kc was also used when we talked about the acids and the bases. Kc is molarity, it's concentration. So we can measure the molarity of a gas. How many moles per liter do we have of this gas? But normally when we're dealing with gases, we don't usually measure in molarity. We can, but often we measure in another way. Think about filling up a tire. We're measuring the pressure. So often we measure pressure, and we do have K values for pressure, and that's called a Kp. Now, it's written, it looks a little strange right now, but let's just kind of work through this. The Kp is the same exact setup. It's products, water and sulfur dioxide, over reactants. And so those reactants are here. And you're just going to take the pressure of the partial pressure of water in this situation, and it's squared. So water squared times the pressure squared of sulfur dioxide divided by the pressure of hydrogen sulfide squared. And you're going to multiply that. It's going to be a denominator also is the pressure of oxygen, but it's cubed. And it's oxygen. So these subscripts are just talking about which pressure are we talking about. So it's just the pressures. It's the same situation. It just looks a little bit different. And that's measured in atmospheres. Right? This expression, pause it. Do yourself a favor, pause it. It might be a little tricky. And this is what you should have got. Note that you don't have a denominator here. Because it's a solid. So this is the KSP. This is the solubility product of what's being formed when things dissolve. Solubility is dissolving in water. So if you put a solid in water, how much of it does it dissolve? Some things don't dissolve completely, so they have a K value for it. And we talk about the solid dissolving. So the solid is always a reactant, so there's never a denominator with KSP. So KSP is the solubility product constant. They do not have a denominator because they're always solid. So the larger the KSP, that would mean big numbers here, would mean the more it dissolves. So a large KSP means it dissolves a lot. A small KSP means it's rather insoluble. And in solutions, we sometimes refer to that when we form things with small KSPs, precipitates, if you guys recall that, precipitates when we talked about solutions. So this is the equilibrium behind precipitates. So in review, we talked about the Kc. The Kc is the concentration, and all those brackets means concentration. So if there's nothing really special about it, it's not an acid, a base, or solubility of a solid, you can refer to it as a Kc. If we have pressures, if we're using the actual pressures or atmospheres instead of the molarity, we can use it as a Kp, and this is in atmospheres. Ksp, just to review, is the solubility constant, how much things dissolve in solution. And remember, there's never a denominator because it's solid in KSPs. Your Ka is the acid dissociation constant. So this is for weak acids because it's a reversible reaction. That's a Ka. If it's a one-way, that's a strong acid. It's just a one-way arrow. Then we have we don't have a K for that. So weak acids has a dissociation constant for the acid. A Kb is a dissociation constant for a base. And the last one I want to talk to you about is a Kw. This is the water ionization constant. So I told you before that water is not a good conductor of electricity, pure water, but normally water has things dissolved in it, salts, so it is normal water is a good conductor, normal water that we deal with, but pure water is not a very good conductor of electricity. Not a very good conductor doesn't mean it's not a conductor. It can conduct electricity, it's just not very good. But if it has no ions on it, you might be wondering when I said that before, how does it conduct electricity? Well, the truth of the matter is water always will have some ions in it. Because water is in an equilibrium with itself. Pure water will dissociate to make hydrogen ions and hydroxide ions, and they will reform to make water. And that is the water ionization constant, which is the Kw. This is the only value that I need you to memorize. The Kw is 1 times 10 to the negative 14th. 1 times 10 to the negative 14th, which means if this is dissolved equal parts hydrogen and hydroxide, it would be 10 to the negative 7th times 10 to the negative 7th makes 10 to the negative 14th. So these are the concentrations of hydrogen and hydroxide, 10 to the negative 7th molarity, extremely small. So there's not a lot of ions in water, but there are always going to be some. And this balance will always come up to 10 to the negative 14th. So if we had more hydrogen, instead of 10 to the negative 7th, remember this is a negative. So if we had more hydrogen, say 10 to the negative 6th, that's 10 to the negative 6 is bigger than 10 to the negative 7. So if we had more hydrogen ions, 10 to the negative 6, then the hydroxide would have to be 10 to the negative 8 because 6 and 8 make the 14. We will get into logarithmic functions later with this, but if we take, if we want to know the logarithmic function of hydrogen, it's called pH because we're talking about the hydrogen concentration. I'm sure you've heard of pH before now. And so if we take the pH, we take the negative concentration. So if it's 10 to the negative 7th, if you got a graphing calculator in front of you, give it a try, 10 to the negative 7th, and you take the log of that, the negative log of that, that is 7. So the pH of 7 is what you have when you have equal parts of these. So neutral water is a pH of 7. You have a pH of 7 and a pOH of 7. Okay. We got 2 workshops for you. So there's this slide. You might want to pause it on here. And then you've got this slide to pause on. So pause here, and then when you're done working this out, start the video and I will go over the answers with you. So pause now. Do it. Don't play around. Press that. I know you're thinking about it. Do it. Okay. All right, you did it. I'm assuming you did it now and you want to know the answers. So let's go over those answers. Come on. Let's do it. So let's do that, guys. Let's go over the answers. So for the first one here, we would be using, so this is a solid dissociating. So this would be an example of a KSP. That would be a KSP because we have a solid and it's dissociating, and it's dissociating into iron, and that's squared times sulfur cubed. The denominator, it's a solid, there is no denominator here. So that's the KSP. So that would be the answer to A. For B, we would have, well, we could say, we have all these, there's really nothing special. It's not a K, KB, KSP. So we can use the generic KC for this, the concentrations of this. The concentrations of this would be nitrogen times hydrogen cubed, because there's a 3 there, divided by ammonia squared. That's one way we can do it. Or another way we could do it is, what if instead of molarity we did the more common way of gases when it was measured in pressure? If it was done that way, we would have a KP. The KP is the same setup, but we're talking about pressure. So we're talking about the pressure of nitrogen times the pressure cubed of hydrogen divided by the pressure squared of ammonia. So that would be the KP for this. So it could be done either way. And that's how you would set that up. So good practice. You should practice both ways. All right, let's look at the next one. Again, we have just gases, nothing going on here. So we have 2 possibilities. We have a KC. We would have the concentration of hydrogen cubed times the concentration of carbon monoxide divided by the concentration of methane times the concentration of water. Or we could do a KP for this, KP, and that would be the pressure cubed of hydrogen times the pressure of carbon monoxide divided by the pressure of methane times the pressure of water. So that's what we could do for that one. All right, so D. Aqueous, look at this. What does that remind you of? What should be ringing the bells? That's an acid. So this is a Ka. The Ka for this would be the concentration of hydrogen ions times the concentration of bicarbonate. CH3 ions divided by the concentration of the H2CO3. There you go. There's no coefficient, so it's just written like that. E, we have this dissociating. Oh, take a look at that. That's making OH, hydroxide, and that's a base. So this is a KB. We have CH3NH3 positive times the OH concentration divided by water is a pure substance, so that's not going to be in my denominator. It's just going to be this guy over here, CH3NH2. All right. And our final answer to question 1 is this one here. Take a look at that. Solids aren't included. So we could do a Kc for this. And there is no numerator, so we're just going to put a 1 there. So it's a little tricky. And the denominator would just be carbon dioxide. So it would just be the concentration of CO2. Or it could be a Kp because it's a gas. We could have been talking about the pressure of carbon dioxide. So that would just be, again, there's no numerator, and this isn't included because it's a solid. So it would just be the pressure of CO2. So it could be done either way. And that's question 1. Question 2. Let's take a look at question 2. Question 2. So using Le Chatelier's principles to predict the change of the following equilibrium reactions. What should be the effect of a constant equilibrium that undergo if these are at equilibrium with these undergoing these changes? I didn't talk about this in this workshop. This is a review from the second workshop, so 13.2. So if this looks foreign to you, I highly suggest you go to 13.2 and practice. There's just more practice with this. So adding more oxygen to this. So you should explain what's happening here and why. So I'm going to talk it through and tell you the key things that you should explain here. So adding more oxygen is adding more reactant. You should mention that. Adding more reactant will make the equilibrium shift to the right. It's like adding water to the left tank will make it move to the right tank. So adding more reactant will make the shift move to the right. The forward reaction will speed up. So it shifts to the right. The forward reaction will speed up and more product will be produced. B, removing water in this reaction. So removing water in this reaction, you should word it this way. You should say that removing product, because water could be anything, it depends on the reaction, so we have to specify is water a reactant or product. So removing product will cause the forward reaction to occur. As you remove the product to balance the K, it's going to have to replace that K, make more of it. So removing the product will make the forward reaction speed up. Will make the forward reaction speed up. It will shift to the right, and more product will be formed. C, increasing the temperature. So this increasing the temperature, we have to know where the energy, because there's either energy is either a reactant or a product in all reactions, and we don't normally write it unless we're talking about energy. So we have to know. So that's why it's written in this one here. So increasing the energy, or the temperature. So if we increase the temperature, we are increasing the energy because energy is temperature. The more energy you have, the higher the temperature, the kinetic energy. So if you increase the temperature, it's like you're increasing the energy. So just think of this as a product, and increasing the temperature means you're adding more product. If it's a decreasing, that would be like removing some product. So how you would word this one, things you need to do. So increasing the temperature, you have to specify what kind of reaction this is. So increasing the temperature in an exothermic reaction, because the reactant has energy, so this is exothermic. So increasing the temperature in an exothermic reaction would cause a shift to the left, because if you add more product, it's going to shift to the left. It's like adding more water on the left side, on the right side will make it shift to the left side. So it shifts to the left. The reverse reaction will speed up and more reactants will be produced in exothermic reactions. So please make sure you put the word exo in your notes. Finally, decreasing the volume in this reaction here. So in this one here, you should have noted decreasing the volume increases the pressure. If you decrease the volume in a gas, it increases the pressure more and more and more. So you should definitely have some tie-in to pressure. So decreasing the volume increases the pressure. And when you increase the pressure, equilibrium will shift to the lesser amount of gas moles. So you have to say that, to the lesser amount of gas moles. So as you decrease the volume, you increase the pressure, and the equilibrium will shift to the smaller amount of gas moles. In this situation, you have 2 gas moles and the reactants and only 1 in the product. So decreasing the volume will increase the pressure. It will shift to have less gas moles, so the shift will be to the right, and you'll produce more product, and the forward equilibrium, the forward reaction will speed up. So those are the answers. I hope you understand. If you got any questions, save them and ask me as soon as you can. Seriously, real soon. Talk to you later.